Hi class, we are on to the next section in chapter 8, chapter 8.3. We're going to be talking about the polar form of complex numbers and DeMoivre's theorem. So, complex numbers basically reside in the polar coordinate system. So every complex number can be plotted as a point in the XY coordinate system. Okay, so the way that we do this is first we let Z be a complex number. Okay, all complex numbers have the form A plus BI, where A and B are real numbers. We can separate this complex number into what is called the real part and the imaginary part, right? So the real part has no imaginary portion and the imaginary portion has no real part. So here A and B are real numbers. RE of Z is the real part, and the real part is that value of A. IM of Z is the imaginary part. So again, A is the real part, B is the imaginary part. So we distinguish this as the real part of our value Z and our imaginary part of our value Z. So again, we can graph these things on the rectangular coordinate system. And when we do so, it forms an angle and a radius for us to use some of the trick that we've been learning, basically, right? So what we do is replace the x-axis with the real axis, and we replace the y-axis with the imaginary axis. Okay. When we plot our point in space, right, we plot the point AB, and the distance from the origin to AB is the length of our line that's created, right? It's basically the length of this value Z, which we call the modulus. Okay. The angle that's formed by plotting this line, this point AB in the complex plane, is called the argument of Z. And we can find this value, the argument of Z, by using tan inverse because we're given the values A and B. So my value of A, right, it's an X value. It's the length of our line that we've plotted times the angle, the cosine of the angle formed, right? My B value, the imaginary part, is the length of Z, the modulus of Z, times sine of theta. So again, A is like an X value and B is basically a Y value. So if we put this on a graph, okay, my X axis turns into the real axis. My Y axis turns into an imaginary axis. So my point AB lies A units away from the origin and B units up from the origin, right? So I go over A and I go up B, and that's where my point will land. I draw a line from this point to the origin, okay? And notice that that creates a nice right triangle for me, right? So this point is AB in this rectangular coordinate system, where the x-axis is now the real axis and the imaginary axis is the y-axis. The length of this line is the modulus of Z, A squared plus B squared, right? If we come back here, okay, the length of Z is A squared plus B squared square rooted, right? It's just the distance formula. The x and the y's, squaring them, adding them together. And then the angle that's formed is called the argument of Z. Let's come back here. Right. I make an angle here of theta. My value of A, so again, this is similar to a unit circle, right? But it's not a circle of length 1, it's a length of Z. So this length here is the cosine of this angle, but it's been stretched out by a length of Z. So the A value is equivalent to the length of this line formed here times cosine of this angle. The Y value is the sine times the modulus. And if I want to find this angle, remember I'm given A and B, right? This is A plus BI, so I know what A is, I know what B is. So in order to find this angle, I'll use those values given. So I'll use the A value and B value and find this angle with tan inverse. Okay, I use my sine and my cosine in order to find that angle. So these three formulas here is how we're going to relate our complex values into the complex plane and relate them with trigonometry. Okay, so these are our three little transformation values that are going to be very, very important for us for the remainder of chapter 8. Okay. The polar form of a plus bi is given by using these equations. So if I want to write it in polar form, I use these equivalencies to transform it into its polar form. So a plus bi is the length of this, the modulus of this number times cosine theta, so the x value, plus the y value times I, right? So I'm really just writing it into polar coordinates. The x value in polar coordinates, the y value in polar coordinates. I still have this I because I'm just changing the form in which I'm representing it, but I'm not changing the values, okay? So here I can pull out that constant value of the modulus, right, the length of that line. So I have modulus z times cosine theta plus I sine theta. Again, theta being the angle that's formed from plotting it in the complex plane. So if I want to put the complex number a plus bi into its polar form, then this is the equation I have. Sometimes this is called cis, since it's C-I-S. If you want to use that notation, that's fine. So a lot of times they'll be written as cis and then the angle, right? The length, cis, angle. That's a short notation for it. I'm okay with that if you decide to use that in this class. However, I will not be using it. Again, this is the polar form. This modulus is found by the square root of a squared plus b squared. And theta is found by tan inverse of b over a. So these three things are how we relate these complex numbers to their polar form. So let's go ahead and do an example. Let's say we have the value 1 minus I root 3. So I typically write the I in front if I have a radical. I do the same thing if this was like 1 minus x squared. I'd have the x squared in front of the root 3. It's just how the notation I tend to use. So this is my polar form, or my complex form. So it's important to identify what's a and identify what's b, right? My a value is 1. My b value is negative 3. Negative square root of 3, I'm sorry. Okay. So now if I want to put this into polar form, I need to follow this guideline, right? My modulus is going to be 1 squared plus negative square root 3 squared. So that'll be square root of 4, or just 2, right? So this has a length of 2, a modulus of 2. The angle formed is negative square root over 3 over 1. Okay. And we know from our exploration of trig that I can really just throw a 2 under both of these to make it a little bit understandable for what this is. So it's really just a pi over 3, but it's negative, so I gotta, move it over to the other side of my graph and find that it's 5 pi over 3. Okay, it's a negative tangent. So if I want to represent the number 1 minus I square root 3 as polar form, it'll be 2 times cosine 5 pi over 3 plus I sine pi 5 over 3. And I'm not going to actually evaluate my 5 pi over 3 in the cosine and sine. I keep it in terms of cosine and sine, right? So this is my value. Now, if I wanted to go the other way, right? Let's say I was given my polar form. If I wanted to write it as a complex number, I just actually evaluate this x and this y. Okay, so for example, here I'm given the polar form and it's asking me to write it in its complex form, right, as a complex number. Well, I need to figure out what the values of 3 pi over 4 is. So I know that this is a negative root 2 over 2, and this is a positive root 2 over 2, because it's really the same thing as, what is that, 135 degrees, right? So I evaluate those values. I get negative root 2 over 2, root 2 over 2, times 4. So multiply times 4, and that turns into a negative 2 root 2 plus 2i root 2. So this was the complex number that gives me this as a polar form of that value, right? This complex number has this polar form. So I can go back and forth either way. I find it's actually it's a lot easier to evaluate a polar form into complex because you're just finding your cosine and sine values and then simplifying, right? Here, for something like this, when we start off in complex, it's a little bit more work because you have to find the modulus, you have to find your angle. Those aren't terrible calculations to do, but you know, we have to really just be familiar with our trig in order to do that. And that's how we go back and forth between polar form and our complex form for a number. Okay. So now let's talk about multiplication and division of complex numbers. So earlier in the series, we talked about how to multiply and divide complex numbers, as well as adding and subtracting. Of course, I think it was way back in chapter 1. However, we're going to talk about multiplying and dividing using complex numbers using their polar form. Okay, so I'm not really going to go over not rationalizing the denominator, but making the denominator real when we try to divide, or that multiplication is the double distribution that we do, right, or the factoring, or the multiplication of binomials. I mean, because we already know how to do that. Okay, so we're going to look at a different way of multiplying and dividing complex values. Okay, so if z and w are both complex values, then z has a polar form of z times cosine theta I sine theta, and w has a polar form of the length of w times cosine phi plus I sine phi. Here I'm using phi instead of theta because they're not necessarily the same angle, right? This complex value will form one angle, and this complex value will form a different angle. That's why their moduli are different as well, right? So theta goes with z. In this case, phi goes with w. So if I want to multiply these two things, I can, yes, in fact, take z and multiply it times w and distribute across each complex value, right? Or I can multiply their polar forms. Now, here it's very obvious that if I want to multiply these two polar forms, I'm still going to have to do some distributions. I'll leave that to you if you want to do it, okay? But it should be very clear, or it shouldn't be very clear. It's not very obvious, to be honest. But if we follow the formulas, we'll come down to something that simplifies to the form of just cosine theta plus phi and I sine theta plus phi. So instead of expanding this out and simplifying and things like that, like we would do with the regular complex forms, it actually simplifies to adding their angle together inside of the cosine and adding them together inside of the sine. So this becomes much, much easier to evaluate. You just multiply their moduli and then the cosine and sine of one single angle that is the sum of the two individual angles. Okay. Same thing for division. If I want to divide one complex value by another, instead of doing the way that we've been doing so far, we can put them into their polar form. And then we have a subtraction formula where we're subtracting the angles of the two respective complex values. Okay. So it makes it a lot nicer if we have their complex form already, or if their complex form is easy to find. Okay. So here, for obvious reasons, we cannot allow w to be 0 because we can't have 0 in the denominator. Okay. So this brings us to DeMoivre's theorem, right? If I can multiply two complex values semi-easily with a single formula in the complex plane, right, the polar form, DeMoivre's theorem allows us to find powers, right? So remember what a power is. Power is just multiples of multiple products of the same value, right? So instead of z times w, we would have z times z. So then this formula here would be z times z, right? If I find z squared, and this would be theta plus theta. So this would be z squared, right? The modulus squared, cosine 2 theta plus I sine 2 theta. If this was z cubed, I would have modulus of z cubed, cosine 3 theta, because it would be theta plus theta plus theta, and theta plus theta plus theta, right? So cosine 3 theta plus I sine 3 theta. So DeMoivre's theorem allows us to find a general form for powers of a complex number. Now, this is very, very nice because finding powers of a complex number otherwise can be very, very, very tedious, right? So think about having like 2 plus 3i to the 5th power. I have to go 2 plus, I have to have a very long sort of polynomial chain that I'm trying to multiply and simplify. It can take a very long time. Here, I just have to find one angle, right? And then I raise that moduli to a power for just that one single complex value. It's actually much, much faster to use DeMoivre's theorem to find powers of complex number than it is to use what we have done before this section in the textbook. Okay, so if I can take powers, I can also take roots, right? Because a root is just a half power or a 1 to the nth power. So the power for the root form is a little bit different, but it's related to the DeMoivre's theorem. Okay, so if I have a complex number in its polar form, n is a positive real number. Okay, so I'm not doing negative roots. Okay, then there are n distinct roots, right? So if you think about it, if you find 27 cubed, the answer is 3, but it's because it's 3 times 3 times 3. So if I take the polar form, I will have 3 different roots, and in this case, it'll be distinct. They will all be different. Okay. So the way that I find this is I call them root 0, 1, 2, up to k. Okay. The way that I find this is I take the modulus 1 over n, right? So the modulus is always to the nth root. For my cosine, I'm going to have theta plus 2k pi over n. My k is going to count from 0 up to basically up to n minus 1. Okay, so if I'm trying to find the third root, the 3 different roots, a cube root for instance, I'm going to have k is 0, k is 1, k is 2, because that's 3 different values, and the last value is 1 less than n. So for the first one, I'd plug in 0, right? The first one would be w0. It would be modulus of z to the nth root, cosine of 0 over n, because my k is 0. So this would be theta over n being 3, right? N stays the same throughout all iterations, but k counts. It goes 0, 1, 2, 3, until n minus 1. Okay, that's the way this works. So k starts at 0, and it continues to count up to n minus 1, because there is 1, 2, 3, n terms. So that gives me n roots, and each of them are different. Okay. So let's find the cube roots of z equals 4 plus 4i root 3. So we have that the modulus of this is each term squared, and then add it together, then take the square root. So 16, 16, and 3. So add these together, and that gives me actually 4 16s, which is the same as 64. Or we can just square root both terms individually, which is 2 and 4, which is 8, right? So the modulus of this complex value is 8. So we want to find the cubed root of this number. So we need the cubed root of 8, which we know is 2. And my angle is going to be b over a. So 4 root 3 over 4. The 4's cancel, and I'm left with root 3. So this is the same as root 3 over 1, which we know is an angle of 60 degrees, or pi over 3. Okay, so I have my modulus, I have my angle. For the first root, we're going to have k equals 0. We're going to call this value w0, right? So if we just look at the angle first, because that's the math that involves the k, is this interior angle. So we'll just kind of look at this each time we progress through, and then we just really end up just plugging that into the cosine, but not actually evaluating, right? We're going to actually keep these roots in their polar form. We can always put them into their complex form if we need to as well. So k equals 0 implies that this angle here that's going to go inside of my cosine and my sine is just theta over n, because when I plug in 0, the 2k pi disappears. So I have pi over 3. My n I know is 3 because I'm doing cubed roots. So pi over 3 over 3. So this turns into pi over 9. Okay. I'm going to look at k equals 1. So I'm not going in a full circle around pi over 9, I'm taking pi over 3, going in a full circle, and then dividing by 3, right? So pi over 3, I'm going to apply 2 pi to that, right? So then that's going to be, what was that, 6 pi, 7 pi over 3, and then divide that by 3. Okay, so I'm going to add 2 pi, so that's going to be 2 pi plus 1 more pi over 3. So there's 7 pi over 3, so this turns into 7 pi over 9. Right, so that'll be the next angle. I do this one more time for 2 because I need 3 of them. 1, 2, 3, starting from 0. Right, 3 minus 1 is 2, so this is where I'm going to stop at k equals 2. So I'm going to have theta plus 4 pi over n. Okay, so this was 4 pi. So if I add these together, this is the same as 12 over 3 pi. Right, so that's 13 pi over 3 over 3, so 13 pi over 9. So I'm going to get out. Okay, so my W0 is 2 cosine pi over 9, I sine pi over 9. W1 is going to be 2 cosine 7 pi over 9 plus I sine pi over 9. And then W2 will be the same, but with 13 pi over 9. Okay, and that's how you find those 3 roots. The important part is finding out those angles that go on the inside. Now, if I want to plot these, the easiest way to plot these is going to be to turn them into complex numbers and plot them in the complex plane. Okay, I didn't do that for you, but I did plot them. Okay, so this is 1, this is W1, and this is W3. Okay, you can take the time to go ahead and turn these into complex numbers yourself and plot them in the complex plane just to verify that the first one is somewhere just before 2 for the x and something just under 1 for the b, I should say, a and b. Okay, W0 is the same thing, a little bit more than -1 and a little bit more than 1 for the b. Okay, and then my W2. So what I want you to notice here, okay, is that all of these points actually lie on a circle. Okay, not only do they lie in a circle, but they lie in a circle and they're equidistant apart. The distance from W0 to W1 is the same as W1 to W2, is the same as the distance from W1 to W0. They all lie in a circle of radius 2. Okay, this point is my original complex value. It lies on a circle of radius 8. Okay, which should be obvious because its modulus is 8, right? So 1, 2, 3, 4, 5, 6, 7, 8, and it lies on that radius. Okay, and the cubed root of 8 is 2, so it should make sense that these 3 distinct roots lie on the circle of radius 2. Also, it's very apparent because of the way that these work, right? Look at what their modulus is. The modulus is 2. Here, the modulus was 8, so this lies on a circle of modulus 8. Okay, because of the radius is 8. Okay, cubed root of 8 is 2, so that's why this lies on a circle, radius 2 for the 3 complex roots. Okay. So again, the complex roots will always be evenly spaced around the circle that has a radius that is the nth root of whatever our complex number is.